This is the second part of a series on vertical axis wind turbines. And there's a link below to the first video in case you haven't seen it yet. I suggest you watch that video before watching this one. In that first video, I showed how to make a more efficient drag type vertical axis wind turbine. And in the course of experimenting, I stumbled on an idea for making a lift type wind turbine. And I began calling the pieces of fabric that I was using sails. And it turns out that's a very good term for them because in this second iteration, they are acting exactly as sails. And I'll first describe how it's constructed and then show you how it was made. Basically, instead of the pizza pans, I started with 2 discs of plywood. And I have an axle running through them. And I got rid of the trash can that I had between them in the first video. And I've attached sails around the edges. And I have 6 of them. And it turns out to work pretty good. And in order to demonstrate how this works, first we have to talk about what's called the point of sails on sailboats. And it's totally applicable to this new iteration of wind turbine. So let's pretend we're on a sailboat with the wind coming in this direction. And let's draw a circle here. And if we have a boat sitting here, there's an area here where the boat can't go. And if the boat's sitting here, the sail's just going to be flopping around in the wind and you're going to go nowhere. This is called being in irons. And it's time consuming to get out of that condition and get going. Now when your boat's heading in that direction, here's your mast, your sail will be like that with the wind hitting the sail and going this way, and the wind will also go around because the sail is acting like a wing. And there's a broad range where that happens, and that's called being on a reach. And when a sailboat's heading this way, it can actually go faster than the speed of the wind due to the lift created by the sails. Now, it's the same thing on this side, just a mirror image. Now, when you're going in this direction, that's called running. And the boom is usually out one side or the other. And if you want to turn more in this direction, you'll reach a point where that boom will suddenly flip over in the other direction. And that's called a jibe. And you got to be careful when you're in that situation. That's where the boom knocks people in the water and hits them on the head and that kind of thing. So when we demonstrate this wind turbine, you'll see the sails luffing when they're directly into the wind, and you'll see them fill and act like a wing, and then you'll see them jibing to the other direction, and then acting as a wing on the other part of the circle. So let's look first at how I made it and arrange things, and then we'll demonstrate the points of sail on this lift type vertical wind turbine. In the previous video, I showed how I painted along the cut lines with a clear acrylic in order to keep the cloth from fraying. And there's what I used, and a small paintbrush. And I decided to reinforce the corners since we're going to be testing a little harder now. And these reinforcements were laid out on the bias. That is, the threads are running this way and that way, and these little squares are cut out at 45-degree angles. So we have threads running in many different directions on these corners. And here on a piece, I punched these and put some tie wraps through them so I could do some pull tests. And they turned out to be pretty strong. And I used a punch like this. This is a 1/8 inch punch. And you just put it where you want it and hit it with a hammer, and it punches out a nice hole. So I then went on and reinforced all the corners of all the sails, and I'll punch those out so that I can assemble our next unit. To make the discs that will hold the sails, I used 2 pieces of 1/4 inch plywood. I clamped them together and then drilled a hole in the center and put in a machine screw and made this out of a piece of wire to put a pencil in and scribe the circle that I wanted to cut out. And since I had 6 sails, it works out perfect to then use that same length to mark off where each sail will start. Now the other holes are the width of the sail, so these are not spaced evenly. It's only the leading edge mounting holes that are spaced using the same radius. So I drilled sets of holes so that I can put tie wraps through the holes and through the hole that's in the corners of the sails. So that'll make them slightly adjustable by tightening the tie wraps as required. Okay, here we are back at our wind tunnel, and here we can see how the sails are fixed using tie wraps, and the leading edge is pulled fairly tight, and the trailing edge, of course, is, because it's longer, it's quite loose. So let's put the fan on low speed and see if this thing will turn. Well, she turns with no problem. So, whoa. Let's look at one sail as we go around here. We'll be looking at this sail right here. And when we reach the jibe point, you can see the sail flips from one direction to the other. as the sail on a sailboat does when you reach the jibe point. And then down here, that sail is on a reach and continues. And there we're headed directly into the wind, so it's flopping like on a sailboat when it's in irons. And then as we come on around, it goes back into the reach configuration. So the sail automatically does everything that happens on a sailboat as it goes around in a circle. So let's crank our wind speed up to the high speed level. And the noise you hear is from the point where the sail would be in irons, where it's flopping in the breeze. Now, if you've been near a flag on a windy day, you'll hear that same noise. And flags are made to be as light as possible, so they will fly in the slightest breeze. Now, in our case here, since we are supporting the sail, this edge could be stiffened or reinforced. Perhaps when the material is hemmed, a rope or cord could be inserted through the hem so that this cannot flop like that and make noise. Also, you notice when a flag gets tattered, it's on the trailing edge where it starts to rip and come apart. And that's from all this kind of action. So on future iterations, this trailing edge should be reinforced. And I think I probably have too much loose material here, that this could be shortened up somewhat to make it a more of a sail shape. Now, when we want to make this thing bigger, we could use this as a hub and add rods sticking out. You know, you could use metal or wood, or PVC pipe is very cheap. So we can make this thing much bigger in diameter and put the sails out on the end of the extension rods. And then we could also increase the spacing between the discs to make it taller vertically. So there's two ways to make it bigger. And of course, as you get out to the larger diameters, the sails should be made wider so that they fill in the area as much as possible. Now, another thing to point out here is we have sails working on the windward side, and the air that goes through works on the sails on the other side. Let me turn the fan on again, and I'll hold it so it can't turn. And I think you see how the sails are blown out on the back side as well as on the front side. So the sail is actually helping even when it's on the back of the unit. And if we totally filled the front with sails, that would prevent that from happening. So I think you want to leave at least half the area open for the breeze to go on through. Well, at this point we sort of have a proof of concept. The actual construction details would depend a lot on how big you're going to make the thing. So whether you stick to discs and have a small diameter and make it tall, or have radial arms and make it large in diameter, the actual details will change somewhat. So we got to know how big we want to make this thing. So here's an equation for the power that's in the wind. And it's power in watts. And it's 1/2, this is a Greek letter rho, and that's the air density in kilograms per cubic meter. And that's typically 1 to 1.2, something in that area. It depends on your altitude, the barometric pressure, the temperature, the absolute humidity. So you can look up rho for various conditions, but I'm going to use the number 1.0 for that. So that'll be on the conservative side. So here we have the wind speed in meters per second, and notice that's cubed. So that's a very important function. And then A is for the area that you want to consider. And in our case, it would be the area, the cross-sectional area of our turbine. So if this represents our turbine, the area would be the width times the height. Now, here in the US, we generally talk about wind speeds in miles per hour. So 10 miles per hour is 4.47 meters per second. So if we wanted 1 kilowatt at 30 miles per hour, our velocity would be 3 times this. So we would take 3 times that number and then cube it. So, but there's another thing we have to talk about first, and that's the Betz limit. It turns out theoretically you can't extract more than 59.3% of the energy from the wind. And if you think that everything is maybe 85% efficiency, all your belts and pulleys and electrical generation, so 0.85 times the 59.3 says for a really good turbine, you have maybe 50% of the number you would calculate here. And I want to be even more conservative and say maybe we're going to achieve 25%. So if we go with that, instead of 1/2 here, we would have 1/8. So to get 1 kilowatt at 30 miles per hour, you can do the math. It's simple algebra. You're going to need an area of 3 1/4 square meters. And that's a height of 1.8 meters and a width of 1.8 meters. And 1.8 meters is about 6 feet. So we would need a turbine 6 feet high and 6 feet in diameter to do that. And it turns out at 38 miles per hour, we would get 2 kilowatts because of that cube function. As the speed goes up, the power goes up drastically. So you have to decide how much power you want and at what wind speed, and then you can figure out how big the thing has to be, and then you can really start designing it. Well, I had hoped to show you our prototype there really whipping around. Normally there's a strong breeze coming down along the side of that building, but the wind didn't cooperate that day. So in the meantime, I'm working on a more practical design that can be produced in a much larger version. And I'll hope to have something done and present a part 3 video here shortly. So in the meantime, I hope you'll click that like button for me, and I hope you'll watch part 3. In the meantime, you could watch one of these videos that's on screen now.